Now, after this very basic introduction of how to come up with micro-benchmarks, let's discuss the next step of the analysis development process. So the next step really you want to take is to test your analysis on real-world programs. Because granted, the micro-benchmarks are good to test whether your analysis handles particular statements well, but they are way too small to really detect scalability issues or other issues that you will encounter in real-world programs. So the robustness and also scalability of your analysis you will only see when you really throw it on real-world programs. And as you at some point anyway want to analyze real-world programs, it is a good idea, obviously, also during development and already during development to run your analysis on real-world programs. Only on real-world programs you will really see some large-scale issues with respect to runtime or memory, or also when you review the results that you get at this first point, you might see, oh well, the precision is not sufficient, I have to improve in that regard, or it just takes forever to analyze even this tiny little example real-world program here, and maybe I can sacrifice some precision, so maybe I, for example, lower the value of k in the k field sensitivity. And yeah, these kinds of things you will only see when you throw onto real-world programs. A selection of real-world programs that we like to use in phasor analysis are typical open source projects such as the bin utils. So the bin utils is a collection of tiny little very useful Unix tools that just have the right size to do some first initial analyses on. And then later on, when those work as expected, you might want to proceed to larger open source tools. In the past, we, for example, also ran our own analyses onto the framework, the phasor framework itself, just to see how the analysis handles itself, basically. That's a fun thing to do at some point. While testing on real-world programs, there are multiple resources that you also can use and should use. So first of all, logging. So it is very helpful to see what your analysis is doing, especially what it was doing just before it crashed, when it crashes. And when it crashes, it will be useful to use a debugger to see what is going on there. And also, even if your analysis seems to run fine, it is advised at least from time to time to use memory safety checkers, for example, valgrind, to check whether you have some undefined behavior in your analysis. So if you just come up with very basic and straightforward flow functions and don't do any fancy stuff, it should be just alright. But if you do some more fancy stuff, or like myself, work on data flow solvers by themselves, it can become really helpful actually to use valgrind to see what is going on. And also when you encounter some strange random crashes, this is also definitely the time where you want to use valgrind. Of course, using loggers and using the debugger and using valgrind will degrade your performance drastically. So for scalability tests, it is not advisable to use those excessively, but you should use those in case of issues that you encounter, or when you operate on not too large test programs. So already here you have a trade-off again to take care of. Alright, another aspect that is quite important to look into are helper analyses. So your own data flow analysis will need some helper analyses in order to do its work properly. Most prominently, we have to mention points 2 analysis here. So points 2 analysis you will need in order to soundly propagate facts in cases where you store something. Like for example, in this code here, when you store the constant value of 42 into p, then you will also have to propagate this value to the aliases of p. And for this, you will have to run a points2 query, and the points2 query then will tell you that p at the statement where the 42 is assigned to the dereference of p is p and q, and then you will be able to draw this further non-distributive edge here to q, and then continue your propagation. And here in the next statement actually you will load this value again from q, and only because you did the points2 analysis here, so the points2 query, you will actually soundly reveal that 42 will end up in B as well. So this is something that you will have to keep in mind when developing analyses. And also another teaser to DECA 2. In DECA 2 you will learn how actually the flow, the solver by himself will be able to take care of this points2 query, and by doing so support you in soundly propagate also at those statements here. So stay tuned for DECA 2 as well. Another helper analysis that is quite important is actually the ICFG. Now, of course, the solver will already resolve possible calls, for example, for you, so that when the call flow function is requested from your analysis, you are already also past the appropriate callee. But sometimes actually in your own data flow analysis, you're interested in special properties of the callee. Like for example, of the whether the called function is a constructor, or whether it is a destructor, or whether it is an intrinsic function that is implemented in LVM, or some intrinsic function of the standard C library. And obviously those intrinsic functions or those special functions you do not always want to propagate into. So you will have some special data flow effect for them, like special summaries, which we will also discuss at some later point in this lecture here. And to determine whether this is indeed such a function that is to be treated specially, that is something that you might want to ask your ICFG for. And what you could also do is actually have other data flow analyses, like sub-analyses, that run as a helper analysis for your own analysis. Like for example, a typeset analysis that might require some constant propagation. So then you would run a constant propagation as a sub-analysis to reveal some possible constant values, and then continue your type state analysis propagation. And actually the interaction of multiple data flow analyses is also some very exciting topic that you will learn more about in DECA 2. So stay tuned for DECA 2. In the following part of this lecture, I will discuss how to properly design call, return, and call to return flow functions. Consider a function call statement like this one here. What do the flow functions for this statement look like? The answer of that is obviously depends. So what does it depend on? It depends on the semantics of the argument passing. And this is highly depending on your programming language, actually. And in the following, I will discuss the semantics for Java, C, and C++. And only after you are aware of those semantics, you can also properly design the flow functions. Let me discuss Java first. Assume you have a method call of foo, like so, where you pass a parameter a, and the signature of foo looks like this. So the formal parameter f is just an int. And let's assume foo is called with a parameter a that is set to 42. So a will have the value 42, and a is a so-called primitive value because it is of a primitive type. And yeah, the primitive value is then copied into the formal parameter of f. So the 42 will end up here in f. But whatever is done inside of the method foo, also if f is modified again, there is no copying back of the value inside of f back to a. So it's only the calling direction. The other case that Java distinguishes is actually when you do not have a primitive value here, but a reference value. So here a is a reference value that references some object, and in that object there is one field here. Let's suppose it's this field here that has the value 42. And now when you call the method foo with a, and a is a reference value, then f will also hold this reference to the very same object. So now if you modify this field here, so maybe if you increment it, then after returning, the reference of f is not copied back to a, but the effect that has been done to this object here will also obviously then be visible by the variable a. Yeah, actually I just realized I should make my camera view a little bit smaller so that you can see all of the essential parts of the slides. So let's continue back with content. So another aspect worth mentioning in this regard here is that those fields could also hold references to other objects. So if the method foo has some data flow effect to one of the transitively referenced objects below here, then of course also those effects will be visible from A as well by just traversing this access path here. Now let's discuss C and C++. In C and C++ there is call by value, but there is also more. But first let's consider call by value here. So we start again with a fundamental data type such as int here. So what does it look like? The variable a will hold the value 42 again, but you will notice that I do not use a circle here, but such a square. This is indicating that variable a by itself is regarded as some memory. So actually you will be able to take the address of variable a and also reference the address somewhere, so store the address of a to a pointer or so. And This is actually something that is not possible in Java. So variables themselves do not have addresses, and you cannot take addresses of objects explicitly, only implicitly by assigning references. And this is actually the core difference really in the memory model. In C and C++, you can access the memory very, very freely. So what happens here when we call the function foo? The value that is inside of A is copied to F. So there will be, in machine code, this will either be some stack memory allocated for the parameter F, or the parameter is passed in a register, depending on the calling convention and also the number of arguments. And but that's details that is not so much of concern at this point here. So again here the value is copied. And the same actually, this is a value copy here. And the same actually happens for composed data types. So now consider you are passing a whole structure here. So A is now not a primitive type here, but it's a structure type of A. So structure or class doesn't really matter. And what happens here is really, so the memory of A reflects again this compound data structure, and now let's suppose we have this field here of this structure that has the value 42. Now when we call the function foo, actually what happens is that the whole data structure is copied over to the argument here. So this can actually be quite a lot of work to do. If you do this in C, this will silently call memcopy. So the memory is of A is copied to the memory of F. Sorry. If it is C++, it might happen that actually a copy constructor is called. So this copy constructor then could do anything depending on the implementation there. So now let's discuss the data flow effects. The field here is copied over to F. So anything that is modified to this field here in the context of foo will not be visible outside of the context, as again there is no back copying. But what could happen actually, so this again this is the actual object copy here, as I mentioned before. But what could happen really is that one of the fields is a pointer that points to some other object, like so, for example. So now, if you have this address of O, for example, here in this field, then you will be able to reach this other object here in memory. And now if you alter this field 13 here in this object inside of the context of foo, then when you leave the context of foo, you will be visible to encounter this data flow effect also from A via the reference of this field here and reaching this data structure here in memory. So this object here. Now, of course, as I mentioned before in C++, a copy constructor could be called, and actually in C++ even the copy constructor might create a copy of this object here, but this really goes into detail, and this really would be something specific to this particular code. But we should at this point safely assume or soundly assume that this object here might be shared between, might be reachable from both of those copies here, so that we see those data flow effects below here when we further dereference into those fields here. All right. I said there is more in C and C++. The other thing that is possible in C and C++ is call by pointer. So you pass a pointer to the object to the function, and the effect will look like this. So a is a pointer variable that holds the address of some object in memory. So let's call this object O, and then the address of that object is this ampersand operator here, O, so it's ampersand O, and this points to this object here. And now when we call the function foo, the address that is the value of A here is copied to F. So what we see then is actually that the address of O will end up here in F as well, so F does reference this object here. And anything that is modified by foo in this object O will obviously then also be visible from A when we leave the context of foo here. And this might remind you of what you've seen in Java. And actually this somewhat is the conceptual counterpart of what is done in Java. Only difference being that in C, this memory referencing here is done explicitly and you're taking the address, while in Java this kind of pointer stuff is done under the hood and not visible and not really accessible by the developer. So what we do here is a pointer copy. Now, the third possibility that is only possible in C++ actually is call by reference. So sometimes you want to indeed perform some effect of data flow inside of a function with an argument. And what you have to do in C is you will always have to pass the object or variable that you want to modify inside of a function as pointer. Now in C++ it is possible to pass the variable by reference as well, so that you don't have to take pointers and use the propagation or the effect more nicely. So now consider that A is again a variable of some data structure, and now when we call the function foo, then F will actually reference the same object in memory. But as we are analyzing on the intermediate representation level, we are interested in what is really happening on the IR level, obviously, as well. So when we ask Godbold again what such a C++ statement translates to in LVM IR, you will see that under the hood, actually, this is implemented as a pointer as well. So here and after, we do not really differentiate call by pointer and call by reference anymore, as this is basically just the same concept and it's realized in the same way in LVM IR. Only difference that you will see here is actually that you see this dereferenceable attribute here, because the compiler is able to statically ensure that actually you're not passing some weird pointer, so actually not a null pointer here, right? Because on the source level you will provide some concrete variable that you pass by as a reference. So you will know, okay, this is actually not a null pointer and I'm able to dereference it.